Hello everyone, welcome back to the course of electric network. Up to the last lecture, we discussed about transient and steady state response of first order system. In this lecture, we will discuss about the second order system. Now before moving to the topic, I would like to inform you that we have created a group on Telegram where we are providing various resources like notes, assignments, special motivation session, etc. You can join that group to access all those for free. The link to join that group is provided in the description. So let's start our today's topic, which is second order system. Let us consider first series RLC circuit. Our today's first topic, source free second order circuit. Consider first series RLC circuit. This is right, this is R, this is C, and this is L. Now see, in this case the correct state variable will be I. State variable as I. Right. Now writing KVL in this loop, what we will have? We will have IR plus L di by dt plus 1 by C integration of I dt. This part is the drop across this part is the drop across this, and this part is the drop across this element. Right? Now differentiating both sides, we will have what? L d square I by dt square. I am differentiating once again and arranging also 1 by C into IT, isn't it, plus d by dt of IT into R is equal to 0. Now using Laplace transform, we will have what? The Laplace transform of this part will be Ls square Is, where Is is the Laplace transform of this IT. Clear? This will be 1 by C integration. The Laplace transform of IT is Is plus R times S into Is is equal to 0. Taking Is as common, we will have Ls square plus Rs plus 1 by C is equal to 0. Clear? Now see, this part, that is LHS part, is the product of two quantities, two factors, which is Is and this part. Since Is is not 0, because we have already assumed that there was an initial current I, means the inductor was charged and was, after time t equal to 0, it is discharging through this path, right? So this is not 0, so obviously this part will be 0. So Ls square plus Rs plus 1 by C is equal to 0. Once again arranging little bit, R by L into S plus 1 by Lc is equal to 0. This is nothing but the quadratic equation, right? So its root will be, let us say, S1 and S2. What will be S1 and S2? This will be nothing but minus of R by 2L plus or minus square root of R by 2L whole square minus 1 by Lc whole square. Clear? Now let us say this part has one factor and this part is another term. Say alpha is equal to r by 2l and this is omega naught is equal to 1 by root LC. This part is called the damping factor and this part is the called undamped natural frequency, right? So after putting this alpha and omega naught here, our S1 and S2 will be minus of alpha plus or minus root of alpha square minus omega naught square. Now two cases will arise here. Either this part will be greater than, sorry, not two part, three part. Three conditions will be there. First of all, the one of will be this part is greater than this part, or this part is equal to this part, or this part is less than this part, right? Now we will see all these three by one. Now considering the first case, case 1, what is that? Alpha square is greater than omega naught. Alpha is greater than omega naught. Now this part is, this case is called as overdamped condition or overdamped, means r by 2l is greater than 1 by root LC. Now note it here, several questions are asked based on this condition, right? They will give the values of R, they will give a network or circuit and will ask you that comment on the whether it is underdamped, overdamped or critically damped. So for electric networks to be overdamped, second order electric network to be overdamped, this should be the condition. Now if this is the case, then what will happen? If this is case, then obvious this part will be positive and lesser than this part, means the two roots will be negative and real and also unequal, right? Then what will happen? Then nothing but taking inverse Laplace transform, it will be of the form of, it will be some constant a1 e to the power s1t plus some constant a2 e to the power s2t, right? Now what is a1 and a2? a1 and a2 are some constants which should be determined from the initial condition. Now considering case 2, what is that? If these two factors are, these two terms which we are calling alpha and omega naught are equal, this case is called as critically damped, right? Star mark here. For that what we will have, r by 2l is equal to 1 by root of LC. This is the condition for an RLC series circuit to be critically damped. In that case, our two roots will be negative, real and equal, right? Then what will happen? IT will be of the form of A1 plus T A2 e to the power minus alpha t. Now moving to our third case, case 3, if alpha is less than omega naught. This is called underdamped. If this is the situation, what will happen? R by 2L will be less than omega naught, which is 1 by root LC. Clear? In this case, our two roots will be complex conjugate with negative real part. Clear? And in that case, our solution will be IT is equal to e to the power minus real part of t, that is alpha t, A1 cos omega dt plus A2 sin omega dt, where omega d, which is damped frequency, will be nothing but root over omega naught square minus alpha square. This is our damped frequency, right? And what will be the time constant tau? Tau will be nothing but reciprocal of or inverse of the real part, which is nothing but 1 by alpha. 1 by our alpha is what? R by 2L, so 2L by R. Now if you try to plot this response of, or the natural response, or the source free response of second order series RLC circuit, for these three conditions we will have a graph like this. First case, let us start with our third case. Why? Because this will dies. This will be the damped frequency or damped condition or underdamped response, right? This will be the critically damped, and over damped will take longer, right? This will be the over damped, this will be critically damped, and this will be under damped. Basically, damping means the oscillations whose amplitude changes, either increasing or decreasing. Basically, damping means decreasing. So in our daily uses we consider, or we say for our sake, for damping means the amplitude of the oscillation is decreasing. So this is our underdamped response, this is our critically damped, and this is overdamped responses for these three cases: case 1, case 2, case 3, right? Now we will see parallel lattices second order system. parallel RLC circuit, right? This is L, this is C, in this case the correct state variable will be the voltage across capacitor. Now writing KCL, we will have I is equal to C dV by dt plus V by R plus I is what? 1 by L integration of V dt is equal to 0, isn't it? This is the current through capacitor, this is current through resistor, and this is the current through inductor, right? Capacitor current, resistor current and inductor current. Now differentiating this, we will have C d square V by dt square plus 1 by R dV by dt plus 1 by L V, isn't it? Once again, just like the previous one, taking homogeneous Laplace transform, we will have Cs square Vs, where Vs is the Laplace transform of this Vt. I think it will be better to say Vt, because this function and this function are different. Mention it here. Taking Laplace transform, we will have a transform as Vs, and this V and this V are different, means this function and this function are different. So Cs square Vs plus 1 by R S Vs plus 1 by L Vs. Taking Vs as common, we will have S square plus 1 by R into S plus 1 by LC is equal to 0. Basically I have taken Vs as common and dividing by C at the same time, we will have this. Now Vs cannot be 0, so obvious S square plus 1 by RCS plus 1 by LC will be 0. Now the same as previous one, this will have two roots, minus 1 by 2 RC plus or minus root over 1 by 2 RC square minus 1 by root LC square. Now once again saying this term as alpha and this as omega naught. Let us say our alpha is 1 by 2 RC, our omega naught is 1 by root LC. Clear? Just same as previous one. This is undamped natural frequency and this is the damping factor. Same as the previous one, there will be 3 cases depending on the magnitude or the value of alpha and omega naught. Alpha and omega naught. Case 1, if alpha is greater than omega naught. Same as previous one, this will be overdamped, means for an overdamped parallel RLC circuit, this will be the condition. Means if a circuit is given in parallel RLC circuit type, then this circuit to be overdamped, this condition must be satisfied. Now if this condition satisfied, our two roots will be what? Negative, real and unequal, right? And in that case our Vt will be what? Some constant a1 e to the power minus of s1t plus some constant a2 e to the power minus s2t, isn't it? Once again, a1 and a2 will be found by initial condition. Clear? Case 2. What is that? If alpha is equal to omega naught, this will be the critically damped condition. So for a parallel RLC circuit to be critically damped, 1 by 2 RC should be equal to 1 by root LC. In that case, the roots will be repeated. Roots will be negative, real and equal, right? And our Vt will be a1 plus a2t e to the power Vt is equal to a1 plus a2t e to the power minus alpha t, right? Case 3. What is that? If alpha is less than omega naught. If this is the condition, then it will be under damped. Means a parallel RLC circuit to be under damped, this condition must be satisfied. Right? In this case, the two roots will be complex conjugate with negative real part, and our Vt will become e to the power minus of real part of t or minus alpha t a1 cos omega dt plus a2 sin omega dt, isn't it? Once again, this is omega t d as damped natural frequency, which is nothing but omega naught square minus alpha square. This is damped frequency. Clear? Now, this was the response of source free second order parallel RLC circuit and series RLC circuit. Now the questions in GATE related to this is asked, as I told earlier, is simply based on the type of responses, the type of circuit, the conditions for underdamped, overdamped and critically damped, right? For example, if you consider a circuit, let us say this is 10 volts, R, L, and this is C. Here it is a switch which is moving from position A to position B at t is equal to 0, right? This is C is equal to 1 farad, this is L which is 1 Henry, and this is 1 ohm, right? Now the question is, for t greater than 0, what will be the nature of response, right? If we consider this as I, this is I, if we consider this as I, then what will be the nature of this I after time t equal to 0? Now see, first of all we have to check, since this is a series RLC circuit, so we have to find out the values of alpha and omega naught. Since alpha is equal to 1 by 2 RL, so putting the values, we will have R is what, 1, and L is 1, so 1 by 2 is alpha, and omega naught is what, 1 by root LC, means 1 by root of 1, which is nothing but 1 by 1, right? From here we can see that alpha is less than omega naught. This is condition, this is the condition for what? This is nothing but the condition of underdamped, right? So the response will be of this type. Clear? Right? This is a underdamped circuit for time t greater than 0. I take one more example. And this time we will consider parallel RLC circuit. This is 1 by 2, this is 1, and this is 1. U of minus t, this is current source, right? The question is, for t greater than 0, what will be the response? Let us say this is V. For t greater than 0, the type of response of V is what? Right. Since this is the case of parallel RLC circuit, in parallel RLC circuit, what is the value of alpha? In case of parallel RLC circuit, the value of alpha is nothing but 1 by 2 RC. Here R is what? 1 by 2. C is what? 1. Means it is 1. And what is omega naught? Omega naught is 1 by root LC. Means 1 by root of 1 and 1. Means 1. Here alpha is equal to omega naught. So it is critically damped. means the response of Vt for time t greater than 0 will be critically damped. Now you may ask that here no switch is present, then how can I say that this is transient? See carefully that this is u of minus t, which simply means that for time t less than 0 or for time t from minus infinity to 0, the value was 1 of this current source, and at time t equal to 0 it is becoming 0, and after that it remains 0. So at time t equal to 0 a transient is introduced, which is nothing but the source free second order parallel RLC circuit, right? So in GATE exam this type of questions related to second order system will be asked. Now we will see the forced response of second order system, right? Let us consider this circuit: a resistor, an inductor and a capacitor. Let us say the capacitor was voltage V, this is L, this is the resistor R. The switch is getting closed at t equal to 0 and a voltage source Vs is applied here, right? In this case the dominant state variable, or simply the state variable in RLC series circuit, is what? The voltage across the capacitor, right? Since the total response Vt will be what? Since this is a forced response or the response of a second order system with source is nothing but the sum of two responses. The first is steady state response, which is VSST, plus transient response. Clear? Now at t tends to infinity, or when time t tends to infinity, what will be the picture? Switch is getting closed, R will be same, this inductor will get short circuited and this capacitor will become open circuited, which will be notified as V infinity, that is voltage across the capacitor at time t is equal to infinity. So V infinity will be what? Or VSS will be what? Nothing but Vs, right? And since VTR depends upon the elements R, L and C, and in series RLC circuit our alpha will be what? R by 12 and our omega naught will be 1 by root LC, as was in our previous cases. So the total response will become sum of the steady state response and the transient response, right? So Vt will be steady state response, which is Vs plus A1 e to the power S1t plus A2 e to the power S2t. For which condition? If alpha is greater than omega naught, as in the previous case, which is this condition is for what? This is for overdamped or the steady state part plus e to the power minus alpha t into A1 plus A2t. This is when alpha is equal to omega naught, and this condition is for what? critically damped, right? And the third case is Vs plus e to the power minus alpha t a1 cos omega dt plus a2 sin omega dt. This will occur when alpha is less than omega naught, and this is the case of underdamped. Now, if we try to plot these cases, we will have a response like this. This is Vt. Now see, this is the final value or the steady state value. For underdamped condition, it will look like this. The critically damped will settle down quickly, and the overdamped will take more time to reach steady states. Means the overdamped is slow. Overdamped response is slower than the critically damped. This is critically damped response, and this is the underdamped. Right. Okay. Now we'll see parallel RLC circuit. Consider this circuit. A current source, a switch, a resistor, inductor, and a capacitor. This is the switch. This is the step response of second order parallel RLC circuit. I will say, in case of parallel RLC circuit, the current state variable is the current through inductor, right? Same as our previous one, the total response IT will be the sum of steady state response and the transient part, right? Now see, at time t is equal to infinity, this inductor will act like a short circuit, right? And this capacitor will act like open circuit, isn't it? This is Is. So at time t is equal to infinity, or as t tends to infinity, our I infinity will be what? Nothing but Is, because at time t is equal to infinity, the inductor will get short circuit, and a short circuit path is existing across the current source. So total current supplied by this current source will go through or will flow through the inductor at steady state. But for transient, our alpha will be 1 by 2 RC and our omega naught will be what? 1 by root LC. So the total response I of t will be what? It will be the steady state response plus a1 e to the power s1t plus a2 e to the power s2t. For which case? For alpha is greater than omega naught, and this will occur when it is over damped, right? Or for critically damped case, steady state part is plus e to the power minus alpha t into a1 plus a2t. This will occur when alpha is equal to omega naught, and this response is the critically damped response. And the third case is is plus e to the power minus alpha t a1 cos omega dt plus a2 sin omega dt, isn't it? And this condition is when alpha is less than omega naught, and it is known as under damped. So this was the response of a second order parallel RLC circuit and parallel series circuit in different conditions like under damped, critically damped or over damped conditions, and what are the circuit parameters, what will be the circuit parameters for those conditions or for those situations to be occurred. Or we saw that if a circuit is said to be in a state or said to be in a conditions, whether it is under damped, over damped or critically damped, what should be the conditions. So in GATE exam, basically most of the questions will be asked related to this topic in only this format, that whether it is they will give the response and will ask you about the circuit that which shoots best, or they will give you the circuit and will ask what type of the response it will have, etc. So now I would like to stop here this lecture. In the next lecture we will do some problem on this. So now once again I would like to request you to please like, share, comment and subscribe to our channel. Also join our Telegram group whose link is provided in description. Thank you.